Hello, we're the Bleed ID Blood Loss Monitor team. I'm Caitlin Henderson, an electrical engineering major, and I worked on the speaker, button and switch implementation, ADC strain gauge assembly, and CAD modeling for the enclosure.
Hello, I'm Bradley Spencer. I'm an electrical engineering major, and I worked on the microcontroller implementation, voltage regulation, and display integration.
Hello, my name is Justin Wu. I am a computer engineering major, and I worked on the alarm system and embedded programming.
Hello, I'm Stephanie Bias, a computer engineering major. I worked on the UI and also embedded programming. Quantifying blood loss in real time is a step forward in quickly identifying excessive bleeding that may occur during cesarean procedures, preventing postpartum hemorrhage from happening. We chose to further work on the Bleed ID blood loss monitor in hopes of improving the prototype closer to commercial use in Orlando Health Winnie Palmer hospitals. Our main goal is to improve the electrical and computer engineering aspects and refine the overall structure of the MAE iteration of the Bleed ID blood loss monitor. This includes, but is not limited to, reducing the overall size of the device, upgrading from a breadboard to a PCB, remedying exposed wires, implementing an integrated speaker, and having an easily interpretable user interface that shows flow rate and total volume of blood loss.
Our design is focused on a simple and robust device that can be expanded upon as the demands increase, and ESP32 was specifically selected to meet this requirement. Our device receives power from a store-bought 5-volt AC to DC adapter and uses a switching voltage regulator to buck the 5-volt signal down to a 3.3-volt signal. This voltage regulator can output 2 amps without any thermal issues, which allows for future developers to add functionality. We selected a 7-inch Nextine display as it only uses 2 pins to communicate to the ESP32. This frees up pins for expansion while still being very reliable. The screen is preloaded with graphics to reduce the computational load on the MCU. The ESP32 does not need to repeatedly draw the screen. The pre-saved formats are called from memory.
To achieve the goal of a more robust integrated device, the previous USB-connected speaker was replaced with the DB Unlimited speaker. This speaker easily integrated with the PCB and was connected to the ESP32 via a pinout with pulse width modulation. By utilizing LED-C-Write in the code, we were able to manipulate frequencies for the speaker alarm sounds. We were tasked with eliminating exposed wires and improving the usability of the device. This was accomplished by designing a new enclosure for the device, implementing operating room-friendly buttons, and upgrading the user interface. Additionally, changes were made to the ADC strain gauge assembly to improve stability. The buttons and switches we chose are all waterproof and dustproof, allowing for sanitization. We upgraded the monitor case so that it can be mounted on a telescoping arm or shelf in the operating room.
The Nextine editor, which is a development software, was used to create a GUI. A key part of our design approach is to meet customer requirements and take user feedback into account. Customer requirements include creating a GUI that is easily interpretable at a glance. This includes updating values in the monitoring process using RTOS, where on one hand, we have a core running the calculation of the flow rate and total volume of blood loss, and on the other core currently running is the displayment of these calculated data, as well as being able to trigger alarm indicators when certain danger thresholds are met. Additionally, part of our design approach is to consider and implement features that intend to improve the user's experience. These include designing the functionalities of certain buttons, how to implement user input, and how to display data effectively.
Testing was conducted without access to the medical rail the device will attach to. We improvised, and as a result, our initial testing revealed a consistent negative bias. The bias was due to the improvised mounting of the strain gauge. This was fixed using a vice grip to hold the load cell during testing. This improved our accuracy to plus or minus less than 1%. When used in the operating room, this bias will not be an issue as the device will be hooked to a medical rail.
From testing, we found that long wires cause our data signals to decay. We implemented a short, low-impedance shielded cable to improve data integrity.
From user feedback, we incorporated a touchscreen feature to add redundancy for the buttons. To highlight important information, we adjusted the color of the text. This also provides visual feedback to the user, indicating that the system is actively processing their input.
During our initial testing, our buttons were slow to respond due to our rudimentary implementation of using delays with if statements in our loop. This meant that not only did the user have to wait a while for the system to respond, but also that there was only a small period of time to get that response, meaning sometimes buttons might even register. However, after implementing the use of interrupts, we were able to register the hardware buttons at any time, as well as use a timer to eliminate the use of delays, allowing our latency to be reduced greatly.
Testing also revealed an issue regarding the sequence of data reading and calculation, which negatively affected the processing efficiency. To optimize this, we used RTOS to execute tasks concurrently on both cores of the ESP32.
There are more applications for this device in the future. Real-time blood loss monitoring is needed in most invasive surgeries, not only C-sections. For example, it would be beneficial to accurately track blood loss, which could then affect the administration of medication, such as anesthesia. This device could also be modified and minimized for future use with women who are still in the hospital after a vaginal birth, as postpartum hemorrhaging is still a risk. Hello, this is the Bleed ID blood loss monitor. At this screen, I can adjust our known weight to the 512 milliliters. I've just set that. To tare, we clear any weights from the scale. We press the yellow button when we are ready. It is set, it is cleared. The tare is complete. Now we will place a known weight into the canister, and I will press the yellow button when we are ready. The reading is complete. Now we can remove the known weight from the canister, and I will press the yellow button since we are ready. The removal is complete, and now we can set the flow rate that we wish the alarm to go off, and I will set that to 1 milliliters per second. Next, we select our canister size. Our options are 1,000 milliliters, 1,500 milliliters, and 3,000 milliliters. Our canister is 1,500 milliliters, so I will select the 1,500 milliliters. Now we are ready to begin tracking our blood loss. You can see the blood volume being tracked here. The blood flow rate has exceeded, so our alarm has alerted, and I can disable the alarm sound with the alarm button here or here. Next, we can toggle through the mode of the screen by pressing the mode button. Here you see different views. I've returned to our main screen. Now I can press clear if I would like to clear the data that has been tracked so far, which we have 133 milliliters, which you can see matches our canister. And now I can clear, and we can add to our canister, and any additional blood loss will be tracked. Here you can see our alarm has alerted again, and I will disable the alarm by pressing the button. Next, we will demonstrate meeting the 500 milliliter threshold. Here you can see that we have exceeded the 500 milliliters and triggered the alarm, which I will disable now. Tracking has continued. We could add additional fluid to meet the and that is the threshold met for our blood flow, which is displayed up here. We could add additional blood and meet our next threshold of the 1,000 milliliters, and the alarm will trigger again. We have exceeded the blood flow rate again, which is shown here. It has now alerted us that we are beyond the 1,000 milliliter threshold, which aligns to our canister. And that is the Bleed ID blood loss monitor.